So in this second video, I'm going to continue what I was talking about uh, the convergence, etc. So 1 minute. So what I'm going to do is I want to use these slides. So we last time we had considered some facts about convergence sequences, and I actually gave you a visual picture of what happens. So I was referring to epsilon steady sequences in my last class, which was uh, I said that it's not a standard definition, but I also remarked that it's Terry Tao's book that I was referring to. So let's quickly see what it is. Uh, we first define when do we say two numbers x, y, or epsilon close. So whenever the absolute value of x minus y is less than epsilon, that is the distance between x and y is less than epsilon, then we say the pair xy is epsilon close. So let's return back to now sequences. What I did earlier is just to look at a pair of numbers on the real line, but now let xn be a sequence. We say it is epsilon steady if for all ij, for all pairs ij, xi, xj are epsilon close points. That means you pick any pair of real natural numbers ij, xi, xj should be epsilon close. So one can see that this definition is not exactly what we want for understanding convergence in full generality. For example, even if you look at the simplest one, like the constant sequence, let's say 1, 1, 1, 1. Let's say 1, 1, 1, 1. So we know that this is always constant sequences are convergent, but it doesn't quite say that they are epsilon close. So how do we sorry, I think this is straightforward, but let's say you take any yeah, this one will definitely be epsilon close, but look at others. For example, last time I had given something like 4 2 4/3 1 then 4/5 etc. So this is a sequence we had considered. Now you see, initially you can't get the epsilon closeness. The difference here is 2. The difference here is about 0.3 or something. So uh, you see that this definition doesn't quite suffice. So a sequence xn is called eventually epsilon close if there exists a natural number n naught such that for all I in n xi, for all ij in I think this is probably was for all ij greater than a fixed natural number n naught, xi, xj are epsilon close. So this will help us. Let's see how it. A sequence xn of real numbers is convergent if and only if it is eventually steady for all epsilon greater than 0, which, as I said, translates to the fact that for all xi's, after some sequence element xn naught, all sequence elements cluster around a limit point. And incidentally, the above definition stated in terms of eventual steadiness is equal to the Cauchy sequences. So, which probably in this class I'm not going to deal with, but um, uh, people who are conversant with this definition know that Cauchy sequences are synonymous with convergent sequences. So now we state some simple facts. Every arithmetic progression, if we see it as a sequence, is divergent. So I would like to uh, state it as a proposition. So erase. I just want to see if I can erase my notation, but that's not happening. It's okay. Every arithmetic progression is as a sequence. I want to prove that it is divergent. So first, let us note that by very definition, uh, the an arithmetic progression is monotonic. That is, it is unidirectional. Meaning is either it is increasing or it is if it is progressing towards plus infinity, or it is decreasing, or it's progressing towards minus infinity. In the sense that one can also say that if you consider xn plus 1 and xn, this difference is going to be positive if it is monotonically increasing. On the other way around also, it may be, or it can be negative. But only one of them happens in an AP. Okay, so that's very clear, because if the common difference D is positive, the first one happens. If the common difference is negative, the second one happens. So this cannot be oscillatory. I think I'll stop the share. So you can go to this. Okay, this is a better way to get away from my annotation. So I what I just claimed is that an AP cannot be oscillatory. Now it remains to show that it is not convergent either. So to see that it is not epsilon steady, which was the requirement for convergence, and I'm claiming that is not convergent. So we see that consecutive elements are separated by a distance d. Just a while ago I said. So given any pair xi xj, it's the pair is not epsilon steady because we cannot bound the distance as we vary ij. So that proves our claim. So the next fact that we claim is the following proposition: every convergent sequence is bounded. So let us make a simple definition for this. A set of real numbers is said to be bounded from left if there exists small k in R such that all elements x in the set are greater than k. Okay, it's strictly bounded. Similarly, if there exists k such that x is less than k for all x belongs to S, then it is bounded from right. I should have had a capital K, that's a typo, but anyway. So a set S is bounded or totally bounded if it is bounded both from left side as well as from the right side. So the way I'm putting, you would recognize that I'm trying to visualize the real line and look at bound from the left of the set and right of the set. Okay, so which means boundedness essentially means that you have a large enough interval in which all the elements can be seen to belong to. And a sequence is bounded if the corresponding set is bounded. Okay, so now I'm going first I made a simple definition regarding the set. Now a sequence is bounded if the corresponding set is bounded. What I mean by this is consider the element x1, x2, x3, so on, the infinite set, sequence elements as a set. So now let xn be a convergent sequence. Remember, my claim is that every convergent sequence is bounded. So let xn be a convergent sequence. So by definition, there exists a finite real number L such that uh, the limit of this sequence is limit of xn is L. Or equivalently, we also saw it in terms of epsilon steadiness. So let us consider small k is equal to minimum of these elements x1, x2 up to all that infinite set, and also include the limit, and look for the least value. Okay, so minimum. So this is possible because R is an ordered field, so it's a set. So there's an order on elements of any subset of R. So similarly, let K, capital K, be the max of this set, same set. And now you immediately see that all xi's are lying sandwiched between small k and capital K. And hence, the set of all elements of the sequence is a bounded set, and hence, by my definition, the sequence is bounded. So, hence the proof. So we've proven these two simple facts. The AP is always divergent, and suppose we have a convergent sequence, we can always have a so I think, yeah, I wanted to also say something before I say the end of the video. So what about the converse? So we can all we can also think about the converse. So what is the converse? Given a bounded sequence, is it always convergent? The answer is a clear no, because we know that if you have consider, let's say, yn is let's say some a times minus 1 power n. Now you see, n equal to 1, you get minus a, n equal to 2, you get plus a, n equal to 3, you get minus a. So eventually, as a set, yn is simply a and minus a. And therefore, yeah, well, I should have remarked any finite set is always bounded. So this is a bounded set. And therefore, I mean, any finite set of real numbers. So because it's just having two elements, this is bounded. But it oscillates, so it's not convergent. So this is a counterexample. So what I can say is converse not true. Okay. So I end the lecture here. Thank you.